Hey everyone, and welcome back to this class, Deep Reinforcement Learning, Deep Learning in Python Part 7. In this lecture, we are going to use Q-learning to solve cartpole with quantized states. That means we're going to bin each state so that the set of states is discrete and finite. We'll be using an array to store the Q table. If you don't want to code this yourself, although I highly recommend you do, the relevant file in the course repo is qlearningbins.py in the subfolder cartpole. At the top we have some standard imports, and we have future for ensuring this code is compatible with Python 3. Next we have some functions to help turn the state into a unique number. The buildState function takes in a list of integers and treats them like a string of integers, and returns the integer representation of that string. The toBin function takes in a value and an array of possible bins, and figures out which bin the value belongs in. Next we have the feature transformer class. This is intended to work like a scikit-learn type of feature transformer, where we have a transform function. Note that it only transforms one observation at a time. One other thing to notice in the constructor is that these high and low limits on the bins may seem somewhat arbitrary. I did a little bit of testing, but it definitely wasn't exhaustive. If you really wanted to know what bins you should use, it would be better to take samples from actual episodes, plot a histogram, and look at the range of values you get. Even better would be different size bins, so that the probability of falling into each bin is equal. Also notice how each of the bin limits is created using linspace. We pass in 9 for the size, because 9 splits gives you 10 bins. Remember that anything higher than the max or lower than the min will go to the bins at the edges. Next we have the transform function, which turns one observation at a time into an integer. It makes use of the buildState and toBin functions above. Next we have the model class. The constructor takes in the environment and a feature transformer so that they can be used later. Also inside the constructor is our initialization of the Q table. Its shape is numStates by numActions, since Q is indexed by state and action. The number of states is 10 to the power 4, since there are 10 bins for each of the 4 state variables. The number of actions is just 2. Next we have the predict function. This transforms the state into an integer x, and we use that to index Q. Notice that because Q is a 2D array, if we index it with one integer, we actually get back a 1D array. So here we get back the Q for this particular state, but over all actions. This is useful for Q-learning because we have to take the max of this. Next we have the update function. This takes in a state, action, and target return. First we convert the state into an integer, and then update Q using gradient descent. Next we have the sample action function. This implements epsilon greedy. So with small probability epsilon, we choose a random action. Otherwise, we choose the best possible action using our current estimate of Q. Next we have the play1 function. It takes in a model instance, epsilon for epsilon greedy, and gamma, which is the discount rate. First thing we do is reset the environment so we can go to the start state and initialize some variables. Then we enter a loop. Again, this is capped at 10,000, but if you're using a newer version of Gym, you'll automatically get the done signal after 200 time steps. Inside the loop, we choose an action from the model. We set the previous observation variable to the current observation and then perform the action. Next, we add the reward to our total reward. If we got the done signal, that means the pole has fallen down, or we've reached the limit in newer versions of Gym. If we haven't hit 200 time steps, we set a large negative reward of -300. Next, we update the model using the Q-learning equation using the target return G. When the loop is done, we return the total reward. Next, we have a function for plotting the running average. This is useful because the returns for each episode are going to vary a lot, so it'll be hard to see. We're interested in averaging the returns over 100 episodes, because the OpenAI documentation says your agent is judged by how well it does over 100 episodes. Finally, we get to the main section. The first thing we do here is initialize the environment, feature transformer, model, and gamma. Next, I give you the option of setting up a monitor. All you need to do to get this to work is pass in the string monitor as a command line argument. Next, we play 10,000 episodes. We set epsilon to be 1 over the square root of n plus 1 so that it doesn't fall too quickly. We play the episode, log the total reward, and print our progress every 100 steps. Once we're done the loop, we print our average reward over the last 100 steps and the total number of steps. Then we plot all the total rewards. This plot is going to have a lot of variability, so it's hard to see how well the agent is doing on average. So the next step is to plot the running average as well. Let's run this and see what we get.